The Great Attractor. You're sitting comfortably on your couch, scrolling through your favorite videos, and yet, believe it or not, you're moving at over 1,000,000 miles per hour. Yes, you heard that correctly. Our entire galaxy, along with countless others, is being drawn towards something enormous, something mysterious. This strange pull was first noticed in 1978, and it's been puzzling scientists ever since. It's called the Great Attractor. So, what is this enigmatic force that's tugging at the very fabric of the cosmos? And why is it so hard for us to study? The story of the Great Attractor begins with a riddle. When astronomers started mapping the movement of galaxies in the 1970s, they discovered something astonishing. Galaxies weren't just drifting randomly through space. Instead, they seemed to be moving in a coordinated way, as if an invisible hand was guiding them toward a common destination. Our own Milky Way galaxy, for example, is hurtling through space at a breakneck speed of about 600 kilometers per second, or more than 1.3 million miles per hour, toward a specific point in the sky. This movement isn't just limited to our galaxy, it involves all of the observable universe. So, what could possibly have enough gravitational pull to influence such a vast region of space? 3 words: the Great Attractor. The Great Attractor lies in a region of space known as the Zone of Avoidance. As ominous as that may sound, it's actually the name of the place. The Zone of Avoidance is the part of the sky we cannot see. And the reason why the Zone of Avoidance is unobservable is the Milky Way galaxy, the place in space where we, the humans, live. When we look toward this region, our view is blocked by thick clouds of gas, dust, and stars within our galaxy. It's like trying to see through a dense fog with a flashlight. You only see the fog, and what's behind it remains hidden. For decades, this cosmic curtain prevented scientists from directly observing what lay in the Great Attractor's direction. However, with advances in technology, especially infrared and X-ray telescopes, astronomers have started to lift the veil. So here's the big reveal about the Great Attractor. It isn't a single object like a black hole or a star. It's a gravitational anomaly, a huge region of space where mass is densely concentrated. And this mass isn't limited to visible matter, like stars or galaxies. It likely includes a significant amount of dark matter, the mysterious substance that we are going to talk about later in this video. At the center of this gravitational hotspot lies a massive supercluster of galaxies known as the Norma Cluster. This cluster, along with other nearby clusters, is the reason behind the mighty Great Attractor's massive gravitational pull. Now, you might be wondering, if this thing is so massive, why hasn't it swallowed everything up like a giant cosmic vacuum cleaner? The answer lies in the universe's constant tug-of-war between gravity and expansion. While the Great Attractor's gravity is powerful, the universe itself is expanding, precisely at 160,000 miles per hour. Beyond the Great Attractor lies another colossal structure called the Shapley Supercluster, which is one of the largest known concentrations of galaxies in the observable universe. So, what does this mean for us here on Earth? The forces at play here have been there for billions of years, far beyond our lifetimes. However, studying phenomena like the Great Attractor helps us understand the massiveness of our universe. So, the next time you gaze at the night sky, remember, you're not just standing still, but rather you are rushing toward the Great Attractor. Planet 9. Imagine this, far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, there might be a planet revolving around the Sun. Yes, a planet. Astronomers call it Planet 9, and its existence is one of the biggest unsolved mysteries of modern astronomy. So, what is Planet 9, and why haven't we seen it yet? The story of Planet 9 begins not with a discovery, but with a puzzle. Neptune was discovered in 1846, and soon after we added it to the drawing of our solar system, speculation started to spread that there might be another planet enjoying a ride around the Sun just beyond Neptune's orbit. Fast forward to the 21st century, astronomers studying the outer edges of our solar system noticed something strange. A group of small, icy objects beyond Neptune, known as the extreme trans-Neptunian objects, or ETNOs, were behaving as expected, and some of them had changed their orbits. Scientists believe there was some unseen force shepherding them, pulling them into these odd trajectories. After years of observation and calculations, 2 astronomers came up with a bold explanation in 2016. There might be a giant planet in our solar system that we haven't discovered yet. They called it Planet 9. Here's what we know about this mysterious planet. Planet 9 is thought to be a giant ball of gas, just like its neighboring planets, Neptune or Uranus, and is estimated to be about 5 to 10 times the mass of Earth. As for its distance, think about somewhere between 400 and 800 times farther than Earth's orbit. To put that in perspective, it could take Planet 9 10,000 to 20,000 Earth years to complete just one orbit around the Sun. But if it's so massive, why haven't we seen it? That's where things get tricky. Planet 9's distance and its potential location in the farthest corner of the solar system make it incredibly difficult to detect. Unlike the inner planets, which reflect plenty of sunlight, Planet 9, if it exists, is so far away that it would appear faint. Astronomers are searching for it using some of the world's most powerful telescopes, scanning the sky for any signs of this mysterious planet. But, so far, it remains hidden. If Planet 9 exists, it would be a game changer for our understanding of the solar system. It would mean that the solar system is far more than what we have discovered and what we know so far. And if there's one undiscovered planet, who's to say there aren't more? Scientists have been continuously hunting for Planet 9, and some astronomers believe that we might discover Planet 9 within the next decade. So, the next time you look up at the night sky, remember, our solar system isn't only what we are taught in 5th grade. The wow signal. It's a summer night in 1977. While most people are listening to disco or watching Star Wars, a group of scientists at Ohio State University is scanning the skies for signs of extraterrestrial life. And then, it happens. A bizarre, unexplained signal from space is received, sending one astronomer into such a frenzy that he literally writes, "Wow," next to the data. The wow signal was detected on August 15, 1977 by the Big Ear radio telescope at Ohio State University. This wasn't just any telescope. Big Ear was designed specifically for one job: to scan for some of the distant known objects of the universe. For years, Big Ear scanned the skies, and on the night of 15th August 1977, the telescope picked up a powerful 72-second burst of radio waves coming from the constellation Sagittarius. The signal was narrowband, meaning it came from a single, specific frequency. Exactly the kind of signal scientists hoped an intelligent alien civilization might send. Astronomer Jerry Ehman was reviewing the data when he saw the numbers on the printout spike dramatically. He got so excited that he grabbed a red pen and circled the sequence 6EQUJ5 and wrote the now famous WOW next to it. So how did the scientists know that the WOW signal was different from other signals they had received? First, it was incredibly strong, about 30 times stronger than the background noise of space. Second, it came from the so-called waterhole frequency, a quiet part of the radio spectrum that's ideal for interstellar communication. And third, it didn't match any known natural phenomena, like pulsars or quasars. But here's the catch. The signal only lasted 72 seconds. Big Ear couldn't move to track it because the telescope was fixed, and by the time the Earth's rotation moved the signal out of view, it was gone. Poof! Just like that. Scientists tried to detect it again, scanning the same region of space dozens of times over the years, but to no luck. So, what could it have been? Well, let's explore some possibilities. Option 1. Aliens. This is the fun answer. If an advanced civilization wanted to get our attention, sending a strong, focused radio signal would be a pretty good way to do it. But why would they only send it once? Were they shy? Did their intergalactic Wi-Fi cut out? We may never know. Option 2. A human-made signal that bounced back to Earth. This theory suggests the WOW signal was actually caused by a military satellite or a rogue piece of Earth-based equipment. Option 3. A natural phenomenon we don't yet understand. Space is enormous and we are still discovering unexplored stuff out there. And then there's option 4. Jerry Ehman just got really excited about a glitch. In the decades since, the WOW signal has become a symbol of the search for extraterrestrial intelligence, or SETI. In 2017, a researcher named Antonio Paris proposed that the signal might have been caused by a pair of comets passing through the area. It's an interesting theory, but not everyone's convinced. For now, the WOW signal remains unsolved, so the next time you're staring up at the night sky, remember the WOW signal. Who knows? Maybe one day we'll get a second call. The multiverse theory. What if I tell you that while you are sitting on your couch scrolling through YouTube, sipping coffee, somewhere in another universe, there's another version of you? Maybe they are drinking tea instead. Maybe they are gardening. Or maybe they are in the gym lifting weights. Sounds wild, right? Well, that's what's called the multiverse theory. The idea that our universe might be just one of countless others, each with its own laws of physics, history, and possibilities. The universe as we know it is already ridiculously huge. It's 13.8 billion years old, filled with billions of galaxies, each containing billions of stars. That's a lot of space. But what if I told you that everything we see, everything we've ever known, might be just a tiny speck in a much bigger, infinite sea of universes? That's the multiverse idea in a nutshell. Think of it as a cosmic bubble bath, with each bubble being a separate universe. And yes, some of those bubbles might pop, but let's not think about that right now. The multiverse theory isn't just science fiction, and one of its major clues comes from something called cosmic inflation. Shortly after the Big Bang, the universe expanded faster than the speed of light. Some theories suggest that this rapid inflation didn't just create our universe, but countless others too. Let's talk about it from the lens of quantum mechanics now. According to the many worlds interpretation, every time a quantum event happens, like a particle choosing one path over another, it splits the universe into multiple timelines. In one universe, you decided to watch this video. In another, you are currently watching funny cat videos. And let's not forget string theory, the theory that says everything in the universe is made of tiny, vibrating strings. String theory predicts extra dimensions, which opens the door to the idea that there might be entirely separate universes we can't see or interact with. So, is the multiverse real? That's the trillion-dollar question. The multiverse theory is fascinating, but it's also contested. Why? Because it's really hard to prove. By definition, these other universes are separate from ours, so we can't directly observe them. It's like trying to prove the existence of a hidden room in your house, but the room is invisible, soundproof, and doesn't share any walls. The galaxy rotation problem. If you could see the galaxy spring, you'd expect the stars near the center, where there's more mass, to orbit faster than those on the outer edges, right? That's what Newton's laws of motion predict, based on how gravity works. But when astronomers started measuring the speeds of stars and galaxies, they found something totally unexpected. The stars in the outer regions were moving just as fast as the stars near the center. But that doesn't make any sense, because the visible matter in the galaxy, stars, gas, and dust, was all there was, then the outer stars should be moving much slower. The reason is simple. There simply isn't enough visible mass to generate the gravity needed to keep those outer stars moving so fast without flying off into space. This is the galaxy rotation problem, which was first disclosed to the world in 1975 when Vera Rubin and her staff member Kent Ford discovered that most stars in spiral galaxies orbit at roughly the same speed. Rubin's results weren't just surprising, they were groundbreaking. Her work provided some of the strongest evidence yet for the existence of dark matter. So, why don't galaxies behave the way we expect? The answer, it turns out, lies in what we can't see. The leading explanation is that galaxies are surrounded by massive halos of dark matter. Although dark matter is invisible, it does have gravity. And it's this gravity that's holding galaxies together and keeping the outer stars moving fast. Some scientists think we might need to tweak our understanding of gravity itself. The most famous of these ideas is the modified Newtonian dynamics, or MOND, which suggests that gravity works differently on cosmic scales. And then there's the possibility that something entirely incomprehensible is going on in the universe that we don't know about. Scientists are studying the galaxy rotation problem in multiple ways. Advanced telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are providing detailed data on galaxy rotation and structure. Supercomputer simulations are helping astronomers model how galaxies should behave with and without dark matter. Projects like the Large Hadron Collider and dark matter detectors deep underground are searching for evidence of dark matter particles. And some researchers are exploring modified gravity models and other explanations to see if they can make sense of the galaxy rotation problem without invoking dark matter. Although this mystery itself is far from solved, it has led to some of the biggest discoveries in astronomy. Missing baryons. Baryons are particles made up of three quarks, like protons and neutrons. These are the basic ingredients for all the matter around us. Everything you know, from your morning coffee to the moon, is made of baryons. Now, according to cosmologists, baryons make up about 5% of the universe. That might not sound like much, but it's the part we're most familiar with. The rest? Well, that's the dark, mysterious stuff. 27% dark matter and 68% dark energy. But that's a story for another day. Here's the issue. When we tally up all the stars, galaxies, and gas clouds we can observe, we only find about half the baryons. The other half, roughly 50% of the universe's regular matter, is missing. Yes, straight up missing. Imagine you're having lunch and suddenly half of your sandwich is gone. Not eaten, not dropped, just vanished. Well, astronomers have a similar problem. They've lost track of half the normal matter in the universe. And for decades, scientists have been scratching their heads asking, where in the cosmos did it all go? Missing baryons is one of the biggest mysteries of the universe. The question is, where did it all go? One early theory was that the missing baryons might be hiding in galaxies we couldn't see because they were too far away to detect. But advanced telescopes have pretty much ruled that out. So, astronomers turned their attention to the empty spaces between galaxies. And this is where things get interesting. Studies suggest that missing baryons aren't clumped together in stars or galaxies. Instead, they are spread out in a massive, invisible network called the cosmic web. Think of it as a giant spider web stretching across the universe, made of material so thin that it's almost impossible to see. In this case, the web is made of a gas, which is known as the warm-hot intergalactic medium, or WIM for short. And yes, astronomers are really good at making simple things sound complicated. The WIM is made up of extremely hot gas, with temperatures ranging from a few 100,000 to tens of millions of degrees. But why can't we see it? Well, the WIM is so spread out that it doesn't emit much light. It's like trying to spot a single strand of spider silk in the middle of a dense forest. However, scientists have found some clever ways to detect it. Astronomers use a technique called absorption spectroscopy to hunt for missing baryons. Here's how it works. When light from an extremely bright galaxy passes through the WIM, some of the light gets absorbed by the gas. By studying the absorption patterns, scientists can identify the elements in the gas and estimate how much baryonic matter is there. Over the years, this method has provided solid evidence for the WHAM. Observations from X-ray telescopes like NASA's Chandra Observatory have detected traces of missing baryons in the form of highly ionized oxygen. It's like finding breadcrumbs scattered along the cosmic web. In 2020, researchers made a breakthrough when they used fast radio bursts to map out the WHAM. These bursts travel through intergalactic space, getting distorted by the gas along the way. By analyzing the distortions, scientists were able to confirm that the missing baryons are indeed hiding in the cosmic web. Even though we've made progress, there's still work to do. Scientists want to map the WIM more accurately and figure out how it interacts with galaxies and dark matter. Future missions like the Athena X-ray Observatory will help us get an even closer look at this hidden gas. So, the next time you're feeling a little lost, just remember, even the universe can't keep track of all its baryons. The Fermi Paradox. We all tried counting the stars when we were kids. Let me answer one of the most asked questions of our childhood. How many stars are there in the sky? There are about 200 billion trillion stars in the observable universe. That's a 2 followed by 23 zeros. Statistically speaking, many of those stars should have planets, and at least some of those planets should be capable of supporting life. So, where is everybody? This is the Fermi Paradox. It's one question that has kept scientists on the edge of their seats for decades. If the universe is so big and so old, why haven't we found evidence of extraterrestrial civilizations yet? Or, even more disturbing, why haven't they found us? The Fermi Paradox is named after physicist Enrico Fermi, who supposedly asked this very question during a casual lunch in 1950. The story goes that he was chatting about UFOs and interstellar travel when he suddenly asked his colleagues, "Where is everybody?" Fermi wasn't just being nosy. He was pointing out a genuine contradiction. The universe is both massive and ancient, and life, at least on Earth, seems to pop up wherever the conditions are right. So, with billions of years and billions of planets to work with, you would think we'd have at least some evidence of intelligent life by now in some far corner of the universe. In 1961, an astrophysicist, Frank Drake, came up with the Drake equation to evaluate the numerous probabilities involved in the existence of alien life. Drake equation considers factors like the number of stars, the fraction of stars with planets, and the likelihood of those planets supporting life, and then estimates the number of active communicative civilizations in the Milky Way. But here is something interesting about this formula. Depending on how you tweak the numbers, it gives you different results. Add optimistic values and you might get thousands of civilizations. Go pessimistic and you're down to 0. It's like a cosmic lottery where we're not sure how many tickets are even being sold. So, what are the possibilities of an alien civilization existing out there in the cosmic wilderness? Let's talk about it in terms of the different schools of thought about the Fermi Paradox. The first theory is that maybe Earth is special. Maybe life is just really rare, and intelligent life is even rarer. In this scenario, we're the cosmic unicorns and life doesn't exist anywhere except on Earth. Some experts also believe that there might be plenty of alien microbes out there, but they are just that, microbes, and will never be intelligent enough to match humans. Scientists have also suggested that it's possible that intelligent civilizations exist, but they're so far away that their signals haven't reached us, or ours haven't reached them. Or maybe they're using communication methods we don't understand. Another popular belief is that extraterrestrial civilizations are avoiding us. Imagine you're on a safari and you spot a group of lions. Do you run over and introduce yourself? Probably not. Theorists say that advanced civilizations might be intentionally avoiding us, either because we're too primitive or because they have a strict no interfering with freshers policy. Basically, we're the noisy neighbors everyone pretends not to hear. Let's get into the scary stuff. The Great Filter. Introduced by Robin Hanson in 1996, it's an idea that some natural phenomenon makes it nearly impossible for life to evolve from one step to another. It could be the jump from simple to complex organisms, the development of intelligent life, or surviving long enough to explore the stars without blowing yourself up. If the Great Filter is behind us, that's great because it means we have already beaten the odds. But if it's ahead of us, well, we've got a problem. But what if the aliens are already here and have been watching us this whole time? Or maybe UFO sightings and conspiracy theories are all true. Of course, there's no solid evidence to back this up, just a lot of blurry photos and government reports. So, back to Enrico Fermi's question. Where is everybody? The truth is, we don't know yet. And until there is solid proof of extraterrestrial life, you can brag about being the only life present in the universe. Fast radio bursts. Picture this. You are an astronomer, sitting in your lab, peacefully scanning the night sky, when, out of nowhere, you detect a burst of energy so powerful, it briefly outshines an entire galaxy. But this energy burst is over in less than a millisecond, leaving you with just one question. What in the world was that? This is what we know as a fast radio burst, or FRB. These mysterious flashes of radio waves have confused astronomers since they were first discovered in 2007 by Duncan Lorimer and his student David Narkovic. So, what exactly are FRBs and where do they come from? A fast radio burst is a short-lived but incredibly powerful burst of radio waves, lasting just a few milliseconds. Think of it like a cosmic blink, there one moment, gone the next. But don't be fooled by how long an FRB lasts, because even in that tiny fraction of a second, an FRB can release as much energy as the sun does in an entire day. But here's the catch. We don't know what's causing them. Ever since the first detection in 2007, there have been hundreds more of them, with each one raising more questions than answers. Now is the time for the million-dollar question, where do FRBs originate from? The short answer, we don't know. The long answer, we have some theories about what causes them, but there's no proof. Most FRBs seem to originate outside our galaxy, coming from billions of light years away. This means whatever's causing them is really powerful. In 2020, scientists said magnetars, which are a special type of neutron stars, were the source of FRBs. Magnetars have an insanely strong magnetic field, about a quadrillion times stronger than that of Earth. When these magnetic fields shift, they could release bursts of energy that we detect as FRBs. Black holes and their interaction with their surroundings are also believed to be the reason behind fast radio bursts. Maybe a star gets too close to a black hole and gets torn apart, sending out a burst of radio signals that we pick up billions of years later. And then there's the crowd favorite theory, aliens. Some scientists have speculated that FRBs could be signals from advanced civilizations that want to communicate with us. It's an interesting idea, but there's no evidence to back it up, at least not yet. As for why they are hard to study, it's because FRBs are incredibly short-lived, and most of them don't repeat. However, in recent years, astronomers have found that a few FRBs burst multiple times from the same location. For example, in 2012, one fast radio burst, FRB 121MenSO2, was detected to be coming from a repeating source and was traced to a galaxy about 3 billion light-years away. Astronomers are working hard to crack the FRB code. New instruments, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are designed to catch these bursts in real time. CHIME has already detected hundreds of FRBs, helping scientists build a more complete picture of where they come from and how they behave. But what exactly causes these fast radio bursts? Only time and more data will tell. Dark matter. Imagine you're walking through a dark room and you bump into a piece of furniture. You can't see it, but you know it's there because you can feel it. That's what it's like while trying to understand dark matter. We can't see it, we can't touch it, but we know it's out there, shaping galaxies, bending light, and messing with the laws of physics. So, what is dark matter? Why is it so important? And why haven't we figured it out yet? Let's explore this unsolved space mystery. Dark matter is a type of matter that doesn't emit, absorb, or reflect any light. It's completely invisible, but even though we can't see it, we know it's there because of the effects it has on the stuff we can see. Dark matter makes up about 27% of the universe's total mass and energy. To put that in perspective, all the stars, planets, gas clouds, and you only account for about 5%. The rest of it is dark energy, which we will be talking about shortly. So, how do we know dark matter exists? The idea of dark matter first popped up in the 1930s when an astronomer named Fritz Zwicky noticed something weird. He was studying a galaxy cluster and realized the galaxies were moving way too fast. By all rights, the cluster should have flown apart, but it didn't. Zwicky concluded that there must be some invisible mass holding everything together, something providing extra gravity. He called it dark matter, and the name stuck. So, what is the dark matter made of? There have been several theories about the composition of dark matter, with the weakly interacting massive particles, WIMPs, axions, and massive compact halo objects, or machos being the leading candidates. WIMPs are hypothetical particles that interact with regular matter only through gravity and the weak nuclear force. Axions are theoretical particles, much smaller than WIMPs, and machos are regular matter that's just really hard to see. However, they don't seem to make up enough of the missing mass to account for all the dark matter out there. Finding dark matter is like trying to catch a ghost with a butterfly net. But scientists are giving it their best shot, using different methods. Firstly, there are particle detectors that are set up deep underground to catch the faintest interactions between dark matter particles and regular matter. But so far, the results have been quiet. Particle colliders are another attempt by scientists to detect dark matter. In colliders like the Large Hadron Collider, particles are smashed together at near light speed, hoping to create or detect dark matter in the aftermath. And then there is the common method: telescopes and satellites. Hundreds of these are looking for indirect evidence of dark matter, like unusual gamma-ray emissions or the gravitational effects of unseen mass. However, despite all the latest technology and methods, dark matter remains one of the biggest mysteries in physics. Dark energy. What if one day you were flying through space, looking out the window of your starship, and you noticed something odd? Instead of galaxies slowing down as they move away from each other, they were actually speeding up? It's as if the universe has hit the gas pedal for no apparent reason. This cosmic acceleration is one of the most baffling mysteries in all of science. And the culprit? A strange, invisible force we call dark energy. So, what is dark energy? Why is it pushing the universe apart? And how is it messing with everything we thought we knew about physics? Dark energy is a hypothetical form of energy that makes up roughly 68% of the universe. That's right, more than 2/3 of the universe is made up of something we can't see, touch, or directly measure. While we don't know much about it, something we do know is that dark energy is responsible for the accelerating expansion of the universe. Without it, the universe would be slowing down or staying steady, as gravity tries to pull everything back together. Instead, space itself is stretching, and it's doing so at an accelerating rate. Dark energy's story begins in the late 1990s when two teams of astronomers were studying Type Ia supernovae. By measuring the brightness of these supernovae, scientists could determine how far away they were and how fast their host galaxies were moving. What they found was shocking. The galaxies weren't just moving apart, they were doing so at a faster and faster pace. This discovery was like finding out the brakes on your car don't work, and that you're actually speeding up. Scientists were so surprised, they initially thought they'd made a mistake. But after double-checking the data, the results held up. The universe, it seemed, was under the influence of a mysterious force that no one had known about before: dark energy. We don't really know what dark energy really could be, but there's no harm in looking at some of the leading theories about it. Albert Einstein's equation of general relativity had a cosmological constant, which meant he thought the universe was static and needed a little something to counteract gravity. Today's scientists think Einstein's cosmological constant from more than a century ago might actually represent dark energy. Essentially, it's the energy of empty space itself, which is also sometimes called vacuum energy. Another explanation of dark energy is quintessence. No, not the mystical fifth element from sci-fi movies, though that would be cool. It's a hypothetical field that changes over time. Unlike the constant energy of a vacuum, it could explain why the expansion of the universe hasn't always been accelerating, but started doing so billions of years ago. Or maybe dark energy is a completely new form of physics that we don't even have the technology to understand yet. But regardless of what dark energy is, it's an important phenomenon, because what happens next in the universe depends on the properties of dark energy. For example, if dark energy continues to push galaxies apart, the universe will eventually become cold, dark, and lifeless, because stars will burn out and galaxies will drift away from each other. And if this mysterious energy becomes stronger over time, it could completely destroy galaxies, stars, planets, and even atoms themselves. Now, that would be some dramatic ending. From surveying the galaxies to analyzing the cosmic microwave background, and planned future missions like the Nancy Grace Roman Space Telescope, scientists are giving their best shot to studying this mysterious force that makes up 68% of our universe. But, for now, dark energy is a mystery that has kept scientists curious for decades. Black holes. Let's talk about something even more mind-bending now. Black holes. A place where gravity is king, light itself can't escape, and the rules of the universe stop working. First off, what exactly is a black hole? Think of it as a cosmic sinkhole, a region in space where gravity is so strong that nothing, not even light, can escape its grip. The point of no return? That's called the event horizon. Cross it and you're done. There's no escape, no takebacks, and certainly no beam me up, Scotty. The idea of black holes dates back to 1784 when an astronomer, John Michell, published a letter in which he talked about a body so big that even light could not escape. But how do black holes form? Well, most of them are born when massive stars die. When a star runs out of fuel, it can no longer fight against the pull of gravity. The outer layers explode in a supernova, while the core collapses into a point of infinite density, a singularity. That singularity is where all the mass is crammed into a space so tiny, it's almost inconceivable. And around it is the event horizon, the boundary where escape velocity exceeds the speed of light. But not all black holes are created equal. There are stellar black holes, the kind formed from dying stars, which are a few times the mass of our sun. Then you've got the big bosses, supermassive black holes. These are normally found at the centers of galaxies, including our Milky Way, and can weigh millions or even billions of times more than the sun. As for how they get so massive, it's still an open question, and we are still figuring out the answer. Now, you might be wondering, if nothing escapes a black hole, how do we even know they exist? Good question. While black holes don't emit light, their presence is given away by their surroundings. Picture a star orbiting an invisible partner, and if it starts wobbling, chances are there's a black hole nearby. But evidence of their existence came in the form of gravitational waves, ripples in space-time caused by two black holes merging. Detected for the first time in 2016 by LIGO Scientific Collaboration, these waves confirmed that black holes did exist and confirmed Einstein's predictions. Speaking of Einstein, his theory of general relativity predicts black holes, but it also talks about their weirdness. Near the event horizon, time slows down relative to an outside observer. If you were to watch someone fall into a black hole, don't ask why they'd go there, it would look like they were frozen in time. But for the unlucky person falling in, they'd experience the journey as normal. Watch Interstellar and you'll know what I'm talking about. What's inside a black hole? Honestly, we have no clue. The singularity is a place where our understanding of physics completely breaks down. Is it a point of infinite density, or does something even weirder happen there? To find out, we'd need a quantum theory of gravity, a grand unification of the very big and very small, basically everything that exists in the universe. Spoiler alert, we are yet to develop any such theory. But black holes aren't just cosmic destroyers. They might be creators too. Some theories suggest that black holes could be gateways to other universes, whereas the likes of Gerard 't Hooft and Leonard Susskind propose that information swallowed by a black hole isn't lost forever, but somehow encoded on its event horizon, like cosmic hard drives. This idea, known as the holographic principle, is as mind-boggling as it sounds. And here's another interesting information about this space mystery. Black holes don't live forever. Thanks to Stephen Hawking, we know they slowly evaporate by emitting what's called Hawking radiation. Over time, they'll shrink and eventually vanish, leaving behind, well, we're not sure about that part yet. But one thing is for sure, black holes have brought us closer to unlocking the secrets of gravity, space-time, and the universe itself. So the next time you gaze at the stars, remember, somewhere out there, billions of light years away, a black hole might be quietly absorbing light. Wormholes. While we are on the topic, let's talk about wormholes now. Wormholes are something straight out of science fiction. It's a concept so wild it feels like a cosmic cheat code, a shortcut through space-time that could connect two distant parts of the universe or even different universes altogether. A wormhole, also called an Einstein-Rosen bridge, is a hypothetical tunnel connecting two separate points in space-time. Imagine space-time as a sheet of paper. If you fold it so 2 points touch, then poke a hole through them, voila, you have a wormhole! The idea of wormholes comes straight out of Einstein's theory of general relativity. White She was published in 1915. A year later, Austrian physicist Ludwig Flamm realized that certain solutions to Einstein's equations hinted at these space-time tunnels. But it wasn't until 1935 that Einstein and his collaborator, Nathan Rosen, formally introduced the concept in their paper. They described these bridges as solutions to the equations of general relativity, though they didn't think they were traversable. So, how do these mysterious space holes work? In theory, a wormhole consists of two mouths connected by a throat. The mouths could exist in completely different locations, which could be different parts of the universe or even different points in time. The throat is where things get tricky. To remain open and stable, a wormhole would need something called exotic matter. This isn't your average everyday stuff, it's a hypothetical form of matter with negative energy density. Negative energy is to counteract the gravitational forces that would otherwise cause the wormhole to collapse. And here's the million-dollar question. Do wormholes actually exist? Considering we are talking about unsolved space mysteries, the short is, we don't know. This is because there's no observational evidence for wormholes, at least not yet. But they're a valid solution to Einstein's equations, so they're at least theoretically possible. Theoretical physicists like Kip Thorne, who was also consulted for the movie Interstellar, have explored the idea of traversable wormholes. Thorne's work in the 1980s helped define the conditions under which a wormhole could stay open, using exotic matter. But exotic matter itself is a big IF. While negative energy has been observed in certain quantum phenomena like the Casimir effect, we're a long way from producing or manipulating enough of it to stabilize a wormhole. But let's say wormholes are real and we figure out how to stabilize them. What could we do with them? Well, for starters, they make the vast distances of space much more manageable. Instead of spending thousands of years traveling to the nearest star, you could step through a wormhole and be there instantly. It's the ultimate cosmic shortcut. Some theories suggest that if one mouth of a wormhole moves relative to the other, it could create a time difference between the two. In theory, this could allow for time travel, though probably not the kind where you go back and have dinner with Abraham Lincoln. And if the multiverse theory is correct, wormholes could potentially connect not just different points in our universe, but entirely different universes. Imagine stepping into one reality and out into another where the laws of physics are completely different from what we know in this universe. But it's not as simple as it seems. Firstly, we have no idea how to create enough exotic matter to keep a wormhole open. Without it, any wormhole would collapse in the blink of an eye. And even with exotic matter, wormholes might not be stable enough to allow safe passage. The slightest disturbance could cause the whole thing to implode. But even if we were able to create and stabilize wormholes, they would likely be bombarded with high-energy radiation, making them extremely hazardous for travelers. And if wormholes enable time travel, they could also create paradoxes, like the classic grandfather paradox. While we haven't found a wormhole, scientists are exploring the mathematics of wormholes, trying to determine whether they could exist in the real world. Some theories even suggest that tiny wormholes could exist at the quantum scale, connecting different points in space-time on an incredibly small level. Wormholes have captured the imagination of writers and filmmakers for decades. From Star Trek's stable wormholes to Interstellar, space movies are incomplete without wormholes. But while Hollywood often bends the rules of physics for dramatic effect, real wormholes would likely be more complex than anything we have seen on Netflix. For now, wormholes are an unsolved space mystery, but who knows? One day we might unlock their secrets and turn them into highways to travel through space-time. The end of the universe. The universe had a beginning, commonly known as the Big Bang, but like all things, it will eventually have an end. The real question is, what will that end look like? The answer to that question depends on the result of the tug-of-war between two cosmic forces, gravity and dark energy. Gravity pulls matter together, and dark energy pushes everything apart. Right now, dark energy is winning, which is why the universe is expanding at an accelerating rate. But what happens in the future depends on how the behavior of these forces changes over time. Scientists have proposed several scenarios for the end of everything. We'll start with the Big Freeze. Imagine this: the universe keeps expanding forever. Galaxies drift farther and farther apart, stars burn out, and everything grows colder and darker. This is the Big Freeze, which is also called heat death. Now, let's flip the script. What if gravity emerges as the ultimate winner over dark energy? In this scenario, called the Big Crunch, the expansion of the universe slows down, stops, and then reverses. Galaxies begin moving closer together, stars collide, and all matter collapses into an incredibly dense, hot singularity, similar to the state of the universe before the Big Bang. This theory about the end of the universe is called the Big Crunch. Some scientists have even suggested that this could lead to a new Big Bang, creating a cycle of endless expansion and contraction, an oscillatory universe. But what if dark energy doesn't just push galaxies apart, but grows stronger over time? In that case, the universe will end in a manner called Big Rip, where dark energy becomes so powerful that it tears the universe apart. First, galaxies will rip apart, followed by solar systems, planets, and even atoms themselves. Now, let's talk about another possibility, the Big Slurp, according to which the universe might end not with a bang, but with a quantum pop. Quantum physicists say our universe exists in a state of relatively stable energy, but it's possible that this state isn't the most stable. If a tiny patch of space were to quantum tunnel into a lower energy state, it would create a bubble of true vacuum. This bubble would expand at nearly the speed of light, destroying everything in its path. There'd be no warning, it would just happen, and poof, the universe as we know it would be gone. As for the most likely scenario, right now, the evidence suggests that the universe is heading for a big freeze. Observations show that dark energy is driving the universe's expansion, and there's no sign of it slowing down. But we still don't fully understand dark energy or how it might behave billions or trillions of years into the future. Whether our universe ends in a freeze, a crunch, a rip, or a quantum bubble, you don't need to worry, because it won't happen anytime soon. We're talking about billions, trillions, or even quadrillions of years into the future. For now, let's just enjoy learning about the unsolved space mysteries.